Okay, we're going to talk about momentum, or specifically the conservation of momentum in 2 dimensions. So up until this point, we've been taking a linear system. And when I say linear system, again, I mean it can move either left or right. So in the past, maybe you had this object and it would collide directly into this, and it were a completely inelastic collision. This would move on after. So maybe as long as they have the same mass, of course, they would move the same velocity. So this was moving at 20 meters per second. It collides into this. It transfers the momentum. Then this one's going to move at 20 meters per second because of the conservation of momentum. And total momentum must be the same. Alright, but now we're going to look at the conservation of momentum in 2 dimensions. So now we're not only going to line it up, we're not going to line it up perfectly. Now we're going to hit it at arbitrary angles. We can hit them between any 2 angles and see what happens. Now, if you have played, billiards or pool before, you probably have an advantage here because you already kind of know what's going to happen if I do this. What if I just take this red object and I slam it into this? I need to change the order so that there we go. Alright, so what's going to happen if this is coming into here and they hit like this? They just kind of hit like that. Well, if you've played pool before, you know that the red object's going to kind of go off in this direction and the green object's going to go off in this direction. Both are going to go kind of diagonally. So again, what's going to happen is we can kind of anticipate that the red object is going to move like kind of off in this way. Oh, that's not the right color. Kind of off in this way. And the green object's going to kind of move off this way. And this is a really important concept. Now this may seem a little strange because if we analyzed, if this was just at rest before, so let's say this was over here, what is the total momentum in this and before? We don't know the mass and the velocity, so let's just use a generic m and v. So we're going to assume that each of these have a mass of m, so each one has a mass of m, and each one has this one specifically has a velocity of v. Well, you're going to notice that this v velocity is only in the positive x direction. Alright? So there is no, if we're starting to break up momentum into x and y momentum, there is no y momentum right now. Because this object is only moving in the x direction. Alright, so they're going to smack into this, and then all of a sudden it looks like there might be some y momentum because this one's going up and this one's going down. This should actually be fairly reminiscent of the lab that we did, the total momentum lab with the carts, because you had kind of the same process. They were stuck together, there was no momentum. You hit the little spring and all of a sudden they moved, they both were moving. And so you were tempted, and almost everybody said initially, oh, there's some momentum there. But you have to remember that momentum is a vector. And the same thing is applying here. What actually happens is, if we were to break up the momentum of each piece, like this right here, this is momentum, we could break these vectors up, right? And so we would have that there's this piece of momentum and this piece of momentum. And for the green object, there's this piece of momentum and this piece of momentum. And you can kind of see that these are x and y pieces of momentum. We will eventually break these up, but you get the point. At least, conceptually, this is a y momentum, this is a y momentum. But these two y momentums, you'll notice, aren't opposite directions. And since there was no y momentum before, what do you think is going to happen if I took these numbers, if I made actual numbers, and I added these two y momentums, or momenta, together? Well, hopefully you know that they would cancel out to be 0. And if this thing was moving at mv before, right, then when you add this piece and that piece together, you should get mv back out for the total momentum. In other words, in a two-dimensional system, the momentum is going to be conserved in all dimensions. We're not going to do a three-dimensional problem, although if we did, it would be the same thing. It would be pz equals pz prime. So this little notation here, the apostrophe, you may see that like in calculus if you get there, or in physics here. It's just representing a different time, like a different state almost. So if we look at the total x momentum before a collision, or at any point really, as long as we have a system where there's no friction, then the x momentum at some point is going to be equal to the x momentum later. In other words, the x momentum is going to be conserved. Same thing with the y momentum. The y momentum is going to be conserved. So back to our example again, one more time, just so it's a pretty important concept here. If this thing is only moving in this direction, right? This thing is moving like this. And we now know, well, velocity in m, so we know that the total x momentum. So you're going to notice we're going to start breaking up momenta into different x and y values. So in this case, the total x momentum was mv. Well, what that means is afterwards, if I add these two pieces here, let's call this px1, this piece of the triangle right here, and let's call this piece of the triangle px2. If I add px1 plus px2, I should get back out mv, because that was the total x momentum before, right? The total x momentum was mv. Well, these are the only two pieces of momentum, x momentum at this point, and those two pieces together should be equal to mv. If you look at py, we found that py, p total of y, or py total, it doesn't really matter how you want to, what order you want to put those in. But py total at the beginning is clearly 0, right? I mean, this thing is moving, but it's not moving vertically. There is no vertical velocity. It's not going up or down, so the total y momentum is just 0. Which means, again, that after the collision, the total y momentum should be 0 again. So if this is py1 and this is py2, then if I add these two pieces together, notice how they're in opposite directions. Remember, momentum is a vector. So this would be like a positive number, that would be like a negative number. But when I take py1 plus py2, I should get 0 back out. And this is like the fundamental idea behind the conservation of momentum in 2 dimensions, or in 3 dimensions. All right, so let's. One of the really important things is going to be trigonometry. Now I have a video that I'm going to be posting specifically only on the trigonometry, and so when you watch that, hopefully that will help you if you have forgotten. Because, for example, here, calculate the total x and y momenta. I don't know what happened here. So let's go on. I think I should have, I thought I would have an angle. I mean, granted, yes, you could figure out the angle from this. But the total x and y momenta are just going to be 5.3 and 3.2. So I don't know what I did there. Maybe the next one's fixed. No. Oh, here we go. This is what I wanted. Alright, I went the wrong way. Okay, so here, we're trying to calculate, so let's say I want to find out px and py. So px and py. And this was the whole system right here. It was just this one object. So to get px and py, I need to be able to find certain parts of the triangle. Right? I need to be able to find this and this. Now, when you do these triangles, as I'm going to say several times, there's multiple ways to do them. Right now, you have what I would call a velocity triangle. Notice you have a velocity on the hypotenuse. I personally don't like to use velocity triangles. I would rather use momentum triangles. So this hypotenuse, I'm going to relabel with the momentum. And of course, that one equation I said that you should never, the only equation I really think is worth truly memorizing just for the sake of brevity is P equals mv. You're going to have to use that so much. So this side, this total momentum is going to be the velocity, 20 times the mass of 15. So I take 20 times 15, I get 300 kilogram meter per second. So I'm going to actually relabel this hypotenuse. Instead of saying 20, I'm going to label this hypotenuse as 300 kilogram meter per second. Alright, so this is my hypotenuse. Now I want to figure out the x and the y. So let's do, doesn't matter, let's do x first. Notice we have this angle here. So we can use this angle to break up this vector. In essence, we're going back to breaking up vectors. We have a hypotenuse. We have this side of the vector. We have this vector here. And we can use 35 degrees to figure out the horizontal and the vertical components of that vector. Now, all of this comes from SOHCAHTOA, which is why there's a whole video on it. But I will make it much more condensed here and tell you that to get this side, this horizontal side, you're going to have to use the cosine. So this side of the triangle is actually going to be, it's going to be 300 times cosine of 35. And that should give me this side. By the way, don't forget, I should have written this in green, but it doesn't matter. And make sure that your calculator's in the correct mode, so go ahead and check that right now if you're working on this. Hopefully you're working it with me, right? That's the idea. 300 times cosine of 35, I get 245.7. 245.7 kilogram meter per second. Alright, and that is the x momentum. So the total x momentum is just 245.7 kilogram meter per second. The vertical piece of momentum is going to be pretty similar. It's just going to be py. We have to break it up. So 300 times the sine of 15. You'll use sine for py. 300 times sine of 35, I mean. I said 15, I think, but it should be 35. 300 times the sine of 35 gives me 172.1 kilogram meter per second. So you're going to see that you're going to have to use quite a bit of trigonometry in order to figure out these momentum problems. But if this is the only problem, if this is the only object in the system, or at least the only object that's moving, then those would represent the total x and total y momenta. So the px total would be 245.7, and py total would be 172.1. And so then, if there was, so then later, imagine it hit some other object. You know, like let's say there's, I don't know, there's an object here, okay? Obviously, it's kind of in the path, so it will hit this eventually. Well, afterwards, they may go off at arbitrary angles. But again, that conservation momentum says that if you know kind of the different ways that this thing moves, then you can figure out, or you should know that the total y, so if you add this piece, or after they collide, this isn't a good example. I'm sorry, I'm just going to stop right now. But my point was that these will be, the px and py are going to be the same before the collision, and then if there's a collision, even if they're moving at really weird angles or whatever, when we take the two px pieces, when we take the x momenta, they should equal 245.7. When we take the y momenta, they should equal 172.1. Alright, so we're all in the video here. Again, there's going to be another video on the trigonometry, which I'll be posting in just a moment.